Bart Kosko is a professor of electrical and computer engineering and law at the University of Southern California. Dr. Kosko holds degrees in philosophy, economics, applied mathematics, electrical engineering, and law. He has published the textbooks Neural Networks and Fuzzy Systems and Fuzzy Engineering, the trade books Fuzzy Thinking, Heaven in a Chip, and Noise, the edited volume Neural Networks and Signal Processing, Intelligent Signal Processing, and the novels Nanotime and Cool Earth. He is a fellow of the IEEE and the INNS, and he organized the first IEEE International Conference on Neural Networks in 1987 that inaugurated the IJCNN conference series. Well, that's a very impressive resume, Bart. So how did you start all this? How did you get into the field?
Thank you, Dave. I got in the field through my philosophy major and my econ major. The econ major taught me about markets. And the thing about markets is that they reach equilibria, that they equilibrate, and especially when you add multiple agents to them, lots of consumers, lots of producers. There's elaborate math models. I was also a triple major in math on that as an undergraduate, and I was fascinated by that. And the general theory is known as general equilibrium theory, and a variety of results. As you add more players to the marketplace, you get more healthy effects. For example, perfect competition in the ideal case. The demand curve goes flat and things like that, on the one hand. On the other hand, I was an independent major in philosophy with a special focus in logic. And there's just a lot of math and thinking about the foundations of things, including things like multi-valued logic that got relabeled as fuzzy logic. But deeper than that, really in modern philosophy and what launched modern philosophy, kind of the back and forth between David Hume and Immanuel Kant, is worrying about causality. And of course, that's the heart of science, making a causal inference. What is causality? How do you measure causality? And I stumbled across one of my favorite guys in philosophy, his earlier book on philosophy of science, John Stuart Mill. And he put forth some of the first rules for inferring causality from observations, which was in time to lead me to some insights into synaptic learning and especially in causal learning. But that's where I began. It was an interesting combination for me coming out of economics and not being afraid of a big complex system, but diving into it, knowing that often you hit equilibrium. In the market, it's supply equals demand. It was the first time I'd ever seen a Lyapunov function, which a lot of people think somehow is unique to control. No, economists do that all the time in terms of prices. Prices evolve. And so on the one hand, you have that. And the other hand, of just the effects of complexity. So it's an odd background. And I found a researcher who also had an entree into neural networks, for example, by way of markets, and that was Professor Stephen Grossberg. And he had done some early, it wasn't his main thrust, but he had done something on that, and I was fascinated by it. It's very mathematically sophisticated. And I started looking at it. And so it was very natural for me when I looked at neural networks. In those days, this was late 70s, early 80s, often called dendritic trees, that would there be something like supply equals demand? Is there some kind of equilibrium? And the answer is there ought to be, like a thought or a pattern stored in memory. How is that formed? I should also say at the time, David, then as I went into graduate school, it was the peak of the Cold War. And I hope listeners know what that means. But in the United States, about half of scientists and engineers worked in defense. And I was an internal mathematical consultant to the company that at the time was the largest defense contractor in the world, General Dynamics in San Diego. So I was suddenly thrust into these huge weapons programs and lots of experts. I mean, I'd known, for example, about a Kalman filter, which is used in guidance systems for everything, in particular in missiles. And that body of theory, and I'd hear experts talk about what was happening in dendritic theory, and we'd take a look at that. And there was just so much going on in the quote unquote black world. I mean, I had a top secret clearance at age 23, which is crazy, but it's it's true. And I saw that on the one hand. My first day on the job at General Dynamics, again, I was an internal math consultant helping folks. It was like my position. I'd been a teaching assistant at UCSD in math. And my first day on the job was on allocations of multiple cruise missiles to carrier battle groups, something that later was used in the first Gulf War back in the early 1990s. So the complexities, the different tools, and you'd be surprised how many, I say scientists and engineers were there, or at least moonlighted there. And neural networks was something that came up. And I had, as an internal consultant, a chance to absorb the text from libraries, meet with a lot of experts. I met in that context Dr. Robert Heck Nielsen, who ran the research effort at TRW, which had set up an outfit in San Diego for military electronics and avionics. And later with Robert did a lot of things like starting the first neural network conference and like, but that's how I came to it. I had this strange background in market economics. And on the other hand, causal reasoning and philosophy. And the oldest joke is, the most worthless degree you can get is philosophy. Nothing could be further from the truth. Best thing that ever happened to me. And then had the tools. So when I started reading papers on neural networks, it was much harder to follow that material in those days, that I could see what was at issue. But I was really curious. Does a thing equilibrate? What would an equilibrium look like with a brain, with a pseudo brain? Does it depend on the number of neurons? Does it decrease or increase in its performance with the number of neurons and so forth? That's what drove my initial interest in the subject.
Well, with this extraordinarily varied background and all your different interests, what are your most significant accomplishments, do you believe?
And most of what I've done in neural networks have been involving feedback and learning, and especially when they combine. And if you just look at citations, it's primarily in the works, what's called I call it a BAM, or Bi-Directional Associative Memory, I'm happy to tell you about. And it's kind of like something that Stephen Grossberg had with the adaptive resonance theory, the way of interpreting it, and kind of not. And then I was really interested, again, philosophically, in causal networks, and just how complex systems, including political systems, how they collide and combine massive feedback. And it was not clear at all that they would equilibrate. They don't have to. And that led to a whole new theory and a structure. It's very popular now, called a fuzzy cognitive map. In fact, the term is called fuzzy cognitive mapping. I just saw at the University of Cambridge a cognitive map to explain how Brexit in England would affect the energy markets, and so, but it was a way of combining different experts' ideas in causal pictures. Cognitive maps, in some sense, go all the way back to the 1940s, but here, the maps were fed back. Was not an acyclic graph, not a DAG, as computer scientists say, a directed acyclic graph, but it was fed back. And you can combine multiple networks, and on top of that, it was partial. The causality was partial. I thought David Hume and Immanuel Kant and John Stuart Mill would get a huge kick out of all that. But in any event, I did that, and it led me to my first real insight. And that's a thrilling thing when you're a kid. I was in my early 20s. And that was, how do I make an inference between two causal objects? How do you infer a causal directed edge? And it's an intensity. And I called it the differential Hebbian learning law once I'd learned about the models in NeuroWare of synapses and correlation learning of Hebb. But the trouble with Hebbian learning to this day is it simply correlates activities. And so if you set up a Hebbian network, you'll see you get too many spurious correlations. But I saw that as spurious causality. In contrast, I remembered so well that line from John Stuart Mill that we can infer causality. One key method is what he called concomitant variations. Concomitant, like in a product at the same time, or maybe a time lag, and variations. I looked at that, I said, okay, concomitant is a mathematical product. Variation to first order in time is a time derivative. So I took Hebbian learning and put a dot over each of the input, the presynaptic and the postsynaptic neuron, in effect. And therein was born the so-called theory today of the differential synapse. which has a lot of applications. I just saw an application at Harvard on dopamine modeling in the brain. It was not my intent, far from it, especially in the context in the Cold War where this first evolved. Instead, I would take op-eds. I took one from Henry Kissinger and translate the causality assertions of this socio-political expert into a cognitive map. But then the question was how the thing could learn. And so the differential Hebbian learning law was born. Mathematically, if Hebbian learning corresponds to a kind of potential energy structure for a feedback network, differential Hebbian learning corresponds to a kinetic energy type. And there's a relationship there with pros and cons, but it's really seen its biggest applications by far in the non-neural world. Like, for example, modeling things like Brexit, because the alternative, something called a Bayesian belief tree, which can work real well in the small, is just that it's a tree. The thing about causality in the real world, it's all interconnected. And you get 10, 20, 30, 50 nodes connected, representing different causal concepts that you can measure. There's going to be feedback loops, and that makes it real difficult, if not impossible, to deal with the Bayesian belief tree, which is fine when it works, but it's got all kinds of problems. Somebody has to come up with a huge joint probability distribution over, say, 20 nodes. You've got to marginalize those out, and that's computationally very hard to do. And you have other problems with causality. Causality, for example, is transitive. If A goes, like dominoes, A goes to B, B causes C, then A causes C. Well, conditional probability is not transitive in general. And so you got to be careful putting that kind of thing on top of a directed graph. But in the case of neural networks, the search for relationship between feedback and learning took place with what I called a bidirectional associative memory. And one of the original ideas I had for that, I was working with an optics expert, Professor Clark Guest at UCSD. So what if we just let light bounce back and forth between two mirrors? And they went through a spatial light modulator. Would that equilibrate? That kind of idea. And a little bit of math, you come up with something, you have a forward directional energy and a backward directional energy. Would they equilibrate? Answer, yes. Question, when? Answer, always. And so the basic theorem I proved as a kid there is the BAM theorem, is that every real matrix, every n by p matrix of real numbers, every one, no conditions, is bidirectionally stable. That always houses a connection topology between two layers of neurons, where the neurons can have any kind of threshold-like nonlinearity all the way out to the full-blown, what are called Cohn-Grossberg nonlinearities. But certainly for ordinary neurons, not linear neurons, but ordinary neurons, it will always equilibrate. And then moreover, it'll do so exponentially quickly in general. So it's an interesting factoid of that. And it's not surprising people have looked at that to see if it doesn't apply in nature and elsewhere. But the question that I was concerned with, not just equilibration, that was a fairly straightforward question, but what if while it's equilibrating, like two fields of neurons in the brain, what if the synapses start to change? Because when the neurons equilibrate at the fields, you form a pattern, for example, stimulus and response type patterns. And then when you start to encode it in the synapses, which do change in flesh more slowly and also in math models than the neurons, that will tend to undermine the very stable patterns you're trying to encode. And it won't work, it looks like. There is a case where it works. And that case is precisely when there is a Hebbian style correlation learning between the two fields. And that led to something called the ABAM theorem, or adaptive bidirectional associative memory theorem. And it's many, there are literally thousands of papers on these kinds of things out there. But it's one of the few results I'm aware of where you can have any number of neurons. In fact, the more the better in terms of pattern structure. And the time it takes to equilibrate doesn't depend upon the number of neurons. It's like an instantaneous convergence of the network. It's not that, but it's like that because it has exponential convergence in general. And the synapses are constantly changing. So if you go back and look at the underlying networks that are similar to that, the original Hopfield network, which came out at the same time, the early 80s, and Grossberg's extension of that, the Cohn-Grossberg network. In both those cases, you have just one layer of neurons, but you have synapses that are fixed, that are not changing. And we're talking about precisely the case where they changed. The argument for the fixed synapses case is that because synapses change so slowly, to a first approximation, you can model them that way. Okay. But if you look at it, you'll see what asserts itself in its own energy function or Lyapunov function, both forward and backward wise, is literally a correlation between the two fields. And that leads to the A-band model and a whole family of other things that you can extend. And I published one of the first textbooks on neural networks that came out in Prentice Hall back in '91, that was in there. And I kind of moved on after that. Only relatively recently came back. I've been doing a lot of, my career took me elsewhere, in particular to the study of noise, just the general study of noise. What is noise? It's energy, but it's a signal you don't like. Someone else may like it. One person's signal tends to be the other person's noise, just of course you can experience when you're in a restaurant and other people talking. And a lot of us had seen, we took another look at neural networks, that a little bit of dither noise can energize a neural network and improve things. And there had been some results that if you took even back propagation and add slight noise, not a lot, just a little bit of noise to the data, that it would be as if you had a more elaborate optimization. So ordinary back propagation is unconstrained. Adding a little bit of faint noise was as if you had optimization that was constrained with a penalty term or so-called regularizer. And that was an interest unto itself, and I returned to that. And then I hit upon something with respect to maximum likelihood. And this led me to completely come back and reevaluate all that earlier neural network stuff. It takes me much closer to where I am today. And that is this, that most estimation of parameters in science, where we're using data in any way to estimate something, usually numbers in a model. So for example, a sample mean is a classic estimator. A sample variance or covariance is an estimator. And those are the most popular in the world. But when we do that, those are usually estimates that if you set it up as an optimization problem, correspond to the biggest bump in probability. Or if you take the logarithm, the biggest bump in the log probability. And that's maximum likelihood. It's the right side of Bayes' theorem. The left side, often called MCMC or Markov chain, Monte Carlo, different schools call it different things, works even better if you have a description of the parameter prior. But that's kind of where we're headed in the future. We're not quite there. Classical evidence-based medicine, evidence-based science, etc., usually means maximum likelihood if you look at it very closely. Now, if you look at that from the point of view of algorithms, the main algorithm that swallows up the right side of Bayes' theorem is the EM algorithm. The EM algorithm. That's an odd name. The expectation maximization algorithm. It comes from 1979. The great statistician at Harvard, Art Dempster. And the idea is that you're taking one step up the hill, the nearest hill of probability, and there's an adjustment going on, an E and an M step back and forth. It's kind of a two-step process going up. Looked at that and was really, when I was teaching statistics year in and year out at USC, slowly it began to dawn on me, first off, what was really going on there mathematically with the EM algorithm, just how general it is. So for example, it gives birth to most hidden Markov models. It gives birth to almost all the techniques used in classical speech called the Baum-Walsh algorithm, used in hedge funds for estimating prices in the derivatives market in the next few seconds, just like people in speech are trying to estimate what the next phoneme or words will be in a sentence and the like there. But the question arose to me in the case of noise, what noise, David, would make your walk up the probability mountain? You can see a mountain behind me, that's Sugarloaf Mountain, it's 10,000 feet. If that helps, I'm walking up the top of that mountain, and it's an iterative process to get up there. At the top is the peak of probability. It's a solution to my problem, and it's almost, and even clustering problems turn out to have that. What noise would get me up that mountain? It would be the noise that at each step makes the signal more probable, if there is such noise. And it didn't seem like this is not a dither noise. This is not the little faint white noise that we've been adding to neural networks really for decades. Or engineers added, sound engineers, to a music CD so that you can hear things better, that you can take a sine wave that's not quite getting above threshold and get it above threshold. I don't mean that. I'm talking about noise, if there exists such noise, that makes your current signal more probable as you climb that local hill of probability. And I found it. And it's a generalization of the EM algorithm, which again is any kind of maximum likelihood. Well, once I found that, and we filed a patent on it at USC, and amazingly, in the age of the Alice Supreme Court decision, we actually got that patent awarded. That's not my point. My point, though, is I looked at that one day, and then in 2012, I should have seen this earlier, I realized, my God, backpropagation is doing the same thing. Backpropagation has to be the EM algorithm, number one. And number two, given that we just showed these general theorems that we can always noise boost the EM algorithm, we ought to be able to noise boost backpropagation. But that would require a different mathematical formalism. If you just give me a moment here to back up. In San Diego, where I was initially, I'm in Los Angeles, I'm in the mountains here outside of Los Angeles right now. But in San Diego, there was a big, by total happenstance, confluence of neural researchers. I mentioned Dr. Robert Heck Nielsen. I ran the local artificial intelligence group in San Diego, affiliated with UC San Diego, where I would teach, and had also been a student, and a massive concentration of aerospace. There at Coronado Island, just a lot happening there. And in particular, the late great Professor David Romohart, who had a large group of cognitive scientists, and he brought in Stephen Grossberg and many, many other postdocs from Jeffrey Hinton, and a lot of the folks, Michael Jordan, that you've heard of, very talented folks came there, and different people from different backgrounds and the like. And one day, I think it was 84, 85, I was in Romohart's office arguing some point of mathematics with him about something, and he had a bunch of equations on the board. And I said, "What's that?" He said, "Oh, it's just a chain rule." Well, it was the backpropagation equation, which are in fact an instance of the chain rule. Now, when I had David speak to our AI group, I think it was the June gathering of '86, we were already putting together the neural conference and everything. And his book, The Parallel Distributed Processing Edited Volumes, which was a game changer in modern neural networks, was not quite out yet. He had to bring just the book jackets when he talked there. And I had a galley proof of those, and I read it, but there's something that bothered me about it when I read it. I mean, back then when I looked at the presentation, as well written as it was, he was a very good writer. And I looked at the presentation of backpropagation for supervised learning, in particular of the XOR function and things like that. You realize that it was put forth as a deterministic model on its face, and yet there was a clear statement in there that it generalized Bernie Woodrow's model of the least mean square algorithm, which, if folks don't know, it is pound for pound, bit for bit, the most widely used, I think, algorithm in electrical engineering. Any kind of modem, long distance phone call, noise canceller is using that, but it's in effect a one layer linear, sometimes with a nonlinear version of a neural network. So how could you have a model that was a superset, the backpropagation model, deterministic of something that was random? It would have to be random. And then I think people started to see that and realized, well, if I have a bunch of input-output data, these earlier backpropagation networks were used for regression. If I have a bunch of input-output data, that data is not the whole story. Those are just footprints left by random vectors. So the feet are random variables, and they leave footprints, which are the actually observed data. A basic point of statistics. And over time, you did see in the 90s an evolution of backpropagation analyses going from the deterministic simple function approximation regression to a probabilistic approach with classifiers. Okay, but I've been back in more of the Grossberg world, where we had unsupervised things going on and feedback in large numbers. Backpropagations almost always feed forward. You'd say, but wait a minute, there's something called recurrent backpropagation. Yes, there is, but it's really not a straight feedback system. It's introducing like frames in a movie and having sums of gradients inside here. There is something that allows for temporal patterns, but it's not a real feedback thing. It's not like a BAM, not like a bidirectional associative memory or adaptive resonance theory model. And these things are multi-layered and the others weren't. So looking at that hill of probability, it occurred to me one night puffing on a cigar that backpropagation was EM. And as soon as you formulate it that way and realize that it's a maximum likelihood thing, that EM is, again, a two-step walk up a mountain, backpropagation is a two-step walk up some kind of optimization. It looks like cross entropy in one case, it looks like squared error in another. You see, there's got to be a connection. There was. And if I had to boil it down to one mathematical fact, it is this, and it is that Shannon entropy minimizes cross entropy. Well, what does that mean? Shannon entropy is P log P, where P is the probability. But if I have two different probability distributions, two different pictures of the world, P and Q, P log Q is the cross entropy. Now, it's a basic fact of statistics that Shannon entropy minimizes cross entropy. Why? Because the logarithm is a concave function. And there's a famous inequality known as Jensen's inequality. Homework exercises convince yourself that that's true. Now, because Shannon entropy minimizes cross entropy, and because that falls out naturally from any formulation of a conditional probability, that's how one arrives at this EM algorithm, then when you take gradients of it, and you take derivatives, you're taking derivatives of an extremum. So from Fermat's theorem, not the last theorem, but from Fermat's theorem, that means the gradient is null. And because the gradient is null, it nulls out the entropy term. And what you're left with on the one side is backpropagation gradient step. On the other side is exactly the surrogate likelihood of EM. Hence, they're equal. They're the same thing at that value. And that was kind of an interesting insight. So we're able to, with my students and colleagues, we've been able to extend that and apply that. And it's an ongoing research effort. And for me, it was interesting because it starts off with, again, unsupervised learning and BAM-like things. And here's backpropagation, wholly independently being coinciding now with the EM algorithm with max likelihood. And of course, you can extend that in many other ways. Now, my final point about that, what I'm doing here, and I view as a significant accomplishment, was to realize there was a bidirectional structure to backpropagation. We'd missed it. And I've given it the name bidirectional backpropagation. I just wish I'd have seen that back when I was in Dave Rumelhart's office back there in the mid 80s. And here's the idea that in training backpropagation, we're pushing a signal in a classic classifier setting. We have a bunch of input pixels. So we're going to put faces in. We have 10 faces, for example, and push those signals forward to 10 output neurons, which are like 10 light bulbs. And they're encoded in a very special way, very different from what was in the original PDP books, in a so-called soft max way, or mathematically in a Gibbs way, or in the form of an exponential divided by a sum of exponentials. But the effect is it spits out a probability vector. And you're trying to encode it such that, so-called 1NK encoding, that if the third pattern is your face, I got 10 patterns, K equals 10, then I want, whenever I put your face in, I want the third light bulb to come on and the other 9 light bulbs not to come on. I want the third slot in the vector to be 1, the other slots to be 0. That's what you want. That's not what you get. What you get in practice is the probability distribution. You round off to the highest peak. But that's what's happening in the forward to backward direction. And in doing that, the first thing I noticed, and it bothered me really for many years, is that we're ignoring the input layer of a neural network. And I want to stress here, David, that maybe not so much in the INNS world, but in the computer science, Google marketed world, that we're now AI equals neural networks equals classifier network. You know, there's so many other kinds of networks. In that world, people are just ignoring that input layer. But what if you ran it backwards? That's my question. What if, not between 2 layers, but you have 50 deep layers, doesn't matter, and you pass a signal through, you spit out the light bulb, and then run that backwards? Now what's going to happen? In general, noise. You're going to get nothing out of it. And that's why I think people didn't look at that. But I was armed now with this EM insight. And I think one of the reasons people had missed them, you'll see many papers, in the same paper, people discussing backpropagation in the EM algorithm, not realizing there's identity in many cases. Because the EM algorithm talks about M for maximization, a total maximization. We're just talking about partial maximization of a gradient. And in the original 79 paper on EM, that was actually called GEM, or generalized EM. Okay, but for whatever the reason, if you simply train in one direction, then run it backwards, you're going to get noise because you're overriding what would happen in the backward direction. Now, if I can push the math limits of this talk to this level now, if I push signals forward through, I have a probability. It's called the probability of getting this output, namely the light bulb that encodes for your face, the probability of Y given X, given your input face. But then if I go backwards, I have a dual probability, a converse probability, the probability that putting in the light bulb Y, I ought to spit out your face at the input in that backward direction. And something that in Grossberg speak would be a psychological expectation, what the network expects to see given what it's been trained on and given what's stimulating at the input. Okay, but now I've got two probabilities. I got the forward probability and, not or, and the backward probability. That and is a mathematical product, it's not a sum. So I have a forward likelihood and a backward likelihood. Now what happens when I take the logarithm? I get the sum. So the logarithm of a product is the sum of the logarithms. You say, okay, and logarithms maintain the bump structure of the probabilities. That's why when we maximize probability, we work usually with the log likelihood because it's easier, because sums are easier to work with than products, for example. But in any event, that happens. So I have two sums now. I have one sum, log likelihood, which is the old probability log likelihood in the forward direction, one for the backward direction. Their negatives are both errors. And then I have to look very carefully at the neural structure, at the individual layers. So yes, in the forward layer, I'm spitting out softmax neuron outputs. That is a multinomial probability. What is a multinomial? It's the probability of rolling a die. In this case, a 10-sided die. And okay, now the backward direction is what? This is different. I'm mapping back to identity neurons, and that's a regression. And this is what's been missed. So I have a classifier in the forward direction, and I have a regression in the backward direction where I'm doing function approximation, not classifying into individual units. Again, if you go back to the original PDP books, it was presented in terms of regressors. And for a long time, that's how backpropagation was used. So what that tells you is the forward probability is going to be different than the backward probability. Okay, now take the logs. I've done that. Negative the logs give me errors. And if I take, last point, if I take that rolling of a die, that multinomial, that k-sided die in the forward direction, what is its logarithm, negative logarithm? It's the cross entropy. It's that log p log q. And that's why you'll see an overwhelming number of papers at IJCNN conferences and NIPS conferences and every neural conference that they're talking about minimizing the cross entropy. They're dealing with that rolling a die probability. But what about the backward case? Well, when I take the negative of its log probability, that plucks, there's a normal distribution, vector normal description of those identity neurons in regression. And so what we're doing is plucking off the exponent, log of v of x is x. What is the name of the boy whose name is John, as they say? And that's squared error. So it turns out the reason you couldn't get something meaningful in bidirectional backpropagation, because otherwise people surely would have done this. In the forward direction, it's cross entropy for a classifier, but the backward, it's got to go back with the correct structure, which is squared error. Now what happens? The forward direction is trying to learn that probability mapping, but the backward direction is trying to estimate the centroid of you. So if I take your example again, your face, and you're the third category. I've got 10 faces and different samples of those. What's being learned in the backward direction as a regressor is an image of your face, which is the best estimate the neural network can make in a mean squared sense of the sample centroid of all the David Brown samples that it has. If I want to robustify that, then it's a Laplacian, and the statistical version that is called lasso for silly reasons, but it would give you the estimate of the sample median. But fundamentally, that's it. And so when you get the probabilities correct, forward and backwards, just about wrap this point up here, then you see there's kind of like a rudder effect or a tail effect that's being balanced in backpropagation. And you can show here and in generalized adversarial networks and CNNs, these networks tend to perform better. We were simply ignoring the backward direction. So for me, the big results have been the bidirectional associative memory, ABAM, its final extension to supervision with multiple layers forward and backwards, the probability description of bidirectional backpropagation. And then this other work in differential Hebbian learning and causal networks.
Okay, that's very good. For someone who was in very near the beginning of the field, you're still a relative youth. Now, how about your current work?
Working on now a variety of things. One of them I call is Big K. K is the standard term coming out of computer science for the number of patterns in your database, the number of faces that you're trying to recognize, the number of words in your speech recognition problem, the number of videos in your video problem, whatever it is. And if you look at what we have today, David, by and large, K is very tiny. K equals 10, some cases K equals 100. And there are databases that support that. The so-called MNIST database, which is digits written from 0 to 9, or 10 CIFAR images. And there's also CIFAR 100. Now, when you look at it, you got to ask the question, is that scalable? Backpropagation itself, this version of EM, is scalable for this reason, that the complexity of backpropagation in terms of the number n of samples is simply, order n. It is not order n squared, like with a quadratic programming scheme, like support vector machines, or God forbid you have something that's complexity greater than order of n squared. So it's an order n, but the way this particular network is configured, the identity units and several deep layers in just one system, and having this 1 in K encoding in the output, what if you wanted to encode, as we surely will in the future of AI, 1 million, maybe 10 million patterns? I mean, it used to be said that the nose, the olfactory bulb, could recognize 10,000 odors, and now my understanding it's much greater than that. I think that will only grow. What, are we going to still have K equal 100, K equal 1,000? I took another look at that and published this last summer in the 2020 International Joint Conference Neural Network with my student, Oliver Adigan, and to approach something that we call big K. And what's happening here, if you look at it, is that the K many outputs really correspond to the vertices of a K-dimensional simplex, or K plus 1 dimensional simplex, the set of all probabilities vectors of link K. But what that is, that's sitting inside of a hypercube. So if you see my Zoom rectangle here, it's got 4 corners. The simplex just has 2 in this case. The number of corners, the number of binary vectors that have length K, of course, is 2 to the K versus K. So is it possible to use the 2 to the K complexity of the entire cube rather than just, for coding reasons out of the 1990s, just the vertices of a simplex? Answer, yes. And we call it big K encoding. And you can use the same trick that Shannon did back in the mid-40s when he introduced what we call Shannon coding and Shannon codes in general. And that is, I can come up with random codes, because if I take 2 very big bit vectors and pick them at random, it's a big assumption, they, with high probability, will be orthogonal. And there's a whole body of mathematics on that. The more orthogonal those patterns are, the better neural networks work. That's true of feedback systems and feed-forward systems, unsupervised, and the whole shebang. So you want orthogonality. So you can use random, you can't use all 2 to the K, but you can use a big chunk between 2 to the K and K. There's a vast land in there. So you can often get great improvements, but the difference is you can't use the softmax outputs. Well, what can I use? The softmax units today in neural networks correspond again to rolling a K-sided die, maybe a 100-sided die, maybe a 1,000-sided die. Instead, in some sense, you have to go back to the old school approach of the logistic. The logistic neuron, which was, you saw in the work from the 70s into the 80s, was often put forth as a kind of average of real neurons adding up, say, the number of spikes arriving at a neuron in the last 40 milliseconds. But it goes way beyond that. If you look at it mathematically, what the logistic neuron is, it gives you the Bayes 2-class structure between one pattern, cancer and no cancer, tumor and no tumor. If you do that, if you set up, that's an exercise, but if you set up the log odds in terms of a simple Bayesian classifier, Bayes' theorem, I should say, you always get out of that, literally you get out of that the exponential. If you do multi-class classifier, you can get a softmax. Now, if I have, instead of K many output Gibbs network, Gibbs neurons or softmax, if I have the good old-fashioned logistic, which obeys a different structure in its learning law, all this still goes through the connection to EM because of something called backpropagation invariance, or BP invariance. So the same learning law, which is always of the form of an error times a signal, or some function, always error times signal in supervised learning. Whether you're doing logistic regression all the way up to bidirectional backpropagation, regression, and classification. But here's the point. If I have K of those output logistics, what I'm doing is flipping K different coins. It's just that they're all loaded with different probabilities of getting heads. So if you wanted a probability picture and working on that, the old classifiers are rolling a k-sided die, some sides more probable than others, perhaps. But here, if you are willing to extend that to the case of double, it'll be double cross entropy. If you're willing to do that, you'll get the flipping of 10 or 100 or 1,000, whatever k equals coins. And that allows substantial more patterns. In fact, the only problem we're having is we test this on supercomputers that are running literally as we're doing this interview, is finding the test sets, because for whatever reason, the computer science world has been working with tiny k. And this stuff, again, it just doesn't scale. So that's something that we work on. As I mentioned, the general work in noise. But what about the other side of Bayes' theorem? So on the one side, it's maximizing the likelihood. If you look at the other side of Bayes' theorem, you have to have a prior. The prior is the strength and the weakness of Bayes' theorem. It's the Achilles heel of Bayes' theorem. Just like, for example, something else I work in fuzzy logic, the rules, which are a form of priors, are also the Achilles heel. But if you know the prior, it's great. You might say, well, that's avant-garde. Yeah, but if you look at COVID and look at the breakthrough study that appeared in the New England Journal of Medicine, I know because I went over this in my statistics class this semester, on New Year's Eve 2020, it's a historic paper, one of the biggest double-blind, randomized, placebo-controlled trials in history. You will see it is a Bayesian study. It was really quite radical. And it uses the Bayesian conjugacy that we teach between a beta distribution and a binomial. So instead, everyone thinks about flipping a coin in binomial, but modeling the probability of that prior with a continuous curve goes all the way back to the Reverend Bayes. And the upshot is the new posterior is also a beta. And that is literally what is done. And they give you the parameters in there. Take a look at it. I think you'll see that changing. So what happens in this world where there's noise when we go to the other side of Bayes' theorem? It's got a different name. And Markov chain Monte Carlo is that name, or MCMC. Now this comes up in a different aspect we see in neural networks, often of combinatorial optimization. Here's my question for you. How do you search a system for the biggest peaks of the mountain range, or more likely the lowest valleys of cost, if you have millions, trillions, quadrillions of valleys? So you can think of an egg carton that goes out effectively to infinity. How are you going to search that? Here's what you're not going to do, David. You're not going to use convex optimization, which is so popular in signal processing. You're not going to be able to, quote, convexify something. There's just too many bumps, way too many bumps out there. And the only practical way today that we know to search those surfaces is what's called simulated annealing. And that's something Scott Kirkpatrick named an analogy with metallurgy back in the 80s. And it was a feature also in the earlier neural conferences. So if you can have a random ball bouncing and control that bounce with some kind of annealing, you can, in theory, not with high probability, but in convergence and distribution, you can tend to bounce in and get trapped into a deep well. It can take a long time, there's a lot of work on that. Then somebody hit upon this ingenious idea for quantum annealing. And I just published a paper in Physical Review, and you can see it on my website. USC just got awarded a couple of weeks ago a patent on this as well, on simulated annealing and how to noise boost that other side of Bayes' theorem in general, how to extend, which is my real answer to your question, Monte Carlo simulations, of which this is a special case. But the Markov chain Monte Carlo, where we're drawing samples not at random from a random number generator, but according to a correlated Markov chain. But the idea with quantum annealing is, instead of bouncing a ball thermally, to bounce in and out of different cost wells, like if we're trying to minimize the cost of a new wing of an airplane sort of thing. Rather than do that, we could burrow through it with quantum tunneling, an analogy. Now, on the face of it, that seems just absurd, because you'd have to solve Schrödinger's wave equation. Schrödinger's equation, as you know, is only solvable for the hydrogen atom or the hydrogen-like atom. And even then, there's a lot of approximations, and it's a real mess. You know, we don't have a solution, for example, for helium being approximated. But the clever thing about quantum annealing is it allows you to bypass that with an external magnetic field, and there's a whole effort on that. So this isn't the quantum computing people often talk about, of factoring numbers into a product of primes. This is an optimization thing, and it's the cutting edge. So we were able to come up with that noise that makes the quantum annealing more probable, that makes that kind of Markov chain more probable. And so my last point on that is this, that the trouble with these schemes of Markov chain Monte Carlo, that other side of Bayes' theorem, that search for high dimensional optimization, as you will have in genomics, all fields will be facing this as we go deeper into the high dimensional future. The trouble with that is it takes a long time to, quote, burn in. So the saying is in Markov chain Monte Carlo, all roads lead to Rome. In Rome, we're in a kind of thermal equilibrium. Well, how in the hell do we get there is the big question. Because the Markov chain, by definition, is correlated, it takes a long time. It can take 10,000 steps, 100,000 steps. The noise speeds it up. Once you're in Rome, you do ordinary Monte Carlo to estimate your statistics. That's where we are. And so that's that, along with these other things I've mentioned to you. Bidirectional backpropagation is what is largely absorbing my time. If I can just add also the resurrection of fuzzy logic. One of my PhD advisors was the late great Professor Lotfi Zada, who was also involved in neural conferences, the father of fuzzy logic. And there was an earlier era of fuzzy logic when Lotfi developed that at the RAND Corporation. We was at in the summer with the great Richard Bellman of dynamic programming fame. An earlier era, a particular take on it, and a view in a very ad hoc way. I was able to show relatively recently that a bunch of rules for fuzzy function approximation, which always works, by the way, just may take a lot of computation, correspond to probabilities and what's called a mixture probability. And there's actually an EM connection there. So it enables you to combine closed form knowledge that we have in equations by absorbing those into simple probability mixtures with an estimate of what's in your head of what an expert is doing in soft knowledge. And that is, I call fuzzy logic 2.0.
Well, let's change gears here. And if you could briefly say a few words about how our society, the INNS, began and what led up to the formation of the IJCNN series of meetings.
They were tied together. That first neural conference in San Diego, I'll just tell the story quickly. I've told it elsewhere. In June of 1987, in many ways was the big bang of modern neural networks. And like the Big Bang, the noise from it is, the sound from it is still echoing through the professional universe. The Neural Society began, INNS, International Neural Network Society, at that first conference. And it was officially, the Neural Society was set up by Steve Grossberg, who simultaneously set up with Elsevier, thank God, the first big neural publication, neural networks, that continues to this day and hopefully will continue in perpetuity. But the neural conference per se, I set up. And I asked Steve to get involved with that. And I had been, as I said, the artificial intelligence coordinator in San Diego. Something just got dropped on me because of, I don't know, I just was going to several meetings and I was inviting people and someone said, you want to take it over? And I took it over. And I leave the aerospace firm I was at and I go to a small think tank called VERAC. And it was doing high-level research on a variety of subjects, primarily classified, but not necessarily. And there was a lot of that in San Diego. And one day, the president of the company, Chuck Moorfield, himself famous for the Moorfield algorithm and optimization, Chuck knocks on my door and says, how would you like to be the chairman of the San Diego Computer Society? IEEE Computer Society. I said, I don't know. I mean, what do I have to do? He said, well, all you got to do is join the IEEE. And of course, I knew what the IEEE was, but I was not a member of it. It was a little more work to get involved. So I'll write you letters, we'll get you in. And I said, sure. So suddenly I find myself with a vote on the council of a local section of the IEEE. And I had an idea based on what we'd have these gatherings with artificial intelligence every month. I mentioned Dave Rumelhart was a speaker in June '86. Lotfi Zada flew down. A lot of people would fly down because San Diego was one of the few areas in the country that was really doing a big set of diverse, eclectic neural network research. And I said, why don't we have an AI gathering at UCSD? I'll go rent Mandeville Auditorium. And I did for $1,000 on a Sunday. And the local IEEE had, I think, $30,000 in T-bills. And they were talking about, we need to do something. People like San Diego, it's a beautiful city. Let's have a conference on circuits. So I said, let me try this. So I set this up. I borrowed, I think, $2,000 from them. And I needed $1,000 to pay Mandeville. And I gave him back one plus the other. And it maybe made $2,000. And I invited a bunch of vendors who kicked in a couple $100 each. And they got up on the stage. I think there were more people, Dave, on stage as vendors, and there were audience attendees on Sunday afternoon. I remember Dr. Robert Heck Nielsen and me and several other local, and the IEEE were grabbing random walkers by and UCSD and saying, come inside. But it made money. They gave me X and I gave them back 3X or whatever it was. And then around that time, there was an article in Newsweek magazine. In those days, people really read magazines and print things. And there was a picture of John Hopfield, who had just moved to Caltech, and Dr. Robert Heck Nielsen, who again, I said was a TRW, about the new wave and excitement in neural networks. And so I proposed to them, as I'd been thinking for a long time, why don't we have, instead of a circuits, let's have a neural network conference here. It was almost like one of those old Our Gang comedies. Let's put on a circus or something. Let's put on a carnival. And we have so much local talent. And I brought in Robert, who, as someone once described, I think it was Steve Grossberg, said he had a golden mouth. And Robert, a wonderfully persuasive speaker, and he came in and look, here he is in Newsweek too. And we had a vote. That's what it comes down to. You make a motion, it gets seconded, and it passed. And the motion was I could go forth. What did I know? I was 26 years old. I mean, I was barely shaving. I was 26 years old and I was authorized to go forth and negotiate with the biggest hotel in Sheraton Harbor Island in San Diego. But my strategy was this. Had been to the big AI conference the year before at UCLA in Malibu, and I kept their stuff from 85. I still have it in my office. I kept their program. I kept how their plenary speakers. I knew we could buy their mailing list. And I knew for the next year, this was 1986. I knew in 87, they were going to have their big conference in hot, steamy Anaheim in July. Now, I assume that was because Disneyland is the stone's throw there. So I said, well, how about we have it in beautiful San Diego 3 weeks before that? And we did that. And that was the basic strategy, to use the structure of the AI conference. And the AI stuff was wobbling. It's not like today's AI. It was unduly about expert systems. It hadn't produced really any applications, a lot of money, tons of hype, and it was just ripe for competition. And competition it got. And so the auspices of the local IEEE, without any authority, we set up a, quote, international conference. And we got Steve involved and many other people. And we bought the mailing list, and it was an immense gamble. I went down to the Sheraton, just in a nutshell, and I had to sign, which I was happy to do, sign in effect for the whole Sheraton Harbor Island resort. So we would have enough conference space. I said, sure, I'll sign for it. In law, that's calling apparent authority. And, it was a binding contract. By the time the IEEE learned about all this, it was May of 87, and the conference was only a month away. It was too late. They were going to stop it. And it was a big brawl that took place and the like here. But the upshot, I learned the hard lesson that, quote, it's easier to get forgiveness than permission, at least in bureaucracy. So don't ever do this kind of thing again. And by the way, I used that in my novel, Nanotime, which was about a possible World War III, where the foil character is John Stuart Mill. But in any event, that's what happened. So the Neural Conference was a big gamble, but we knew, Dave, and this is the point, we knew the supply was too small. We'd had the precursor to the NIPS conference, which is called the Snowbird Gathering, at 50 people. That was too small. And there was an effort afoot to turn that into what became NIPS. Too small. We needed a journal. We needed a big, eclectic society. And the IEEE, all right, it's a complex thing. If we can combine that with the Neural Society, would get this delicate balance that continues to this day. Really, truly eclectic international conference. But we didn't have much money. And when the IEEE found out it was on the hook for over $1 million, and the initial registrations weren't coming in. But by the time we get to 1987 June, it was a smash hit. They made a ton of money. My understanding was that local section, the IEEE became the wealthiest on the planet in terms of IEEE sections, and they continued the conference series for a while. Then it became a political football, and different groups got involved. And it took a while. It's the nature of birth here. It was very messy. It took a while to stabilize to where we are today. Remember, we had a neural winter after that. We had the old perceptron age in the 60s. It went down. And people rightly or wrongly credit Marvin Minsky's book, Perceptrons, with bringing it down. We had the second wave in the mid-80s that came out, first with Hopfield-style, Grossberg-style networks, but it really was back propagation. Sometimes that's called back hop. And so, for example, at the second neural conference, which I also organized, the question, well, how do you top the first one? Answer, bring in, who was called Darth Vader, bring in Marvin Minsky. Let Marvin give the opening keynote talk. And I hope someone can dig that up somewhere, because it was a delightful talk. He's a wonderful speaker. And then we went through the neural winter. And now we've come back courtesy of ever faster computers, the same old algorithms. Backpropagation really hasn't changed much, despite of what I've been discussing. It's still essentially max likelihood, but the computers are vastly more powerful. They're far more powerful today versus back in 1987 than the gap between 87 and when we were making fun of computers in the 60s. And that continues to this day, and I hope it will continue forever.
Now, jumping from the past into the future, what do you see the role of a society like INNS? What should the INNS be doing?
It should be doing the mission of education, which it has been doing. It has to maintain this balance. And this is not easy. And there have been some really skillful figures that have helped bring this about, to maintain people from, especially a lot of academics, but from different disciplines. I mean, it's bad enough to have an engineering-based society. IEEE is one of the largest, if not the largest, professional societies. Electrical, computers, all those. But there's so many other related disciplines involved here, from neuroscience to different kinds of biology, computational biology, I mentioned quantum computing, linguistics, to bring that together in a format with a lot of people who, you know, at least the organization may not like one another. That's why it was great having the late, great Dr. Robert Hick Nielsen. He's gone now. By the way, I should mention, for those who don't know, Robert created the first neural unicorn, the first neural network company that ultimately made $1 billion. He just passed in 2019.
What was it HCN? What?
HNC,
HNC.
as in Heck Nielsen Neurocomputer Corporation, and which Robert very cleverly launched at that first neural conference, or a few months before that, but the official launch was there. And initially thought he'd be selling hardware devices like IBM, then he realized there's more software. And I think one of their big applications, David, was credit worthiness.
Yes.
You know, you get rejected for your loan, you'd like to know why. The neural network says you fail. It doesn't really have an audit trail. I might add, you asked me what I'm doing. When we combine neural networks with the fuzzy technique, we get what's called XAI, or explainable AI. And we get the probability structure over those rules. So now we still reject you for your loan, but at least you get the consolation of finding out why. Before it was just what the network said. But Robert set that up, then he sold the company, and it became the first such company. It was interesting. It would be like saying, when Newton or Leibniz saying, gee, I want to start a company that sells calculus. That's in effect what was happening with these early all companies have calculus in them. All companies now are using neural networks. But to get back to your question, the primary mission, I think, of the International Neural Net Society, as its name suggests, is education. And first and foremost, maintaining a flagship neural journal, the main one, which is the Journal of Neural Networks, and the international conference and spinoffs. And it does have to be international. This year, for example, the conference is going to be in China. What I would like to see, I've been arguing for years, I'd like to see a major neural conference in India. We haven't had that. I think we could hold it at some of the IIT, the Indian Institute of Technology campuses during the summer. But there's an infrastructure issue there, but at some point that would happen. I also think that the society might want to start a couple more journals, sub-societies. There is such a focus out of the computer science world with this partial renaming of neural networks as, quote, machine learning. We used to have machine intelligence, machine learning. It might not be a bad idea to have a dedicated sub-journal just on that, because you only have so many papers come out per issue. But it's so far worked, you know, went to the fourth decade of this delicate balance between the science world and the engineering world. And by the way, is computer science really a science? I think I put it in the engineering world, but its name says it's a science, but they've always been good with names. I mean, is it really robotics or is it adaptive control? But the science world of biology and neurobiology and quantum and all that sort of thing, and electrical engineering and computer science and the like, and whatever information sciences that come out, we need to have that in the world. We do have that. And so far, so good. It's been extremely well run. I mean, given the ups and downs, the personalities that people have come, we have basically, in that old Greek sense, rebuilt the boat at sea many times now. And that boat is bigger and stronger than ever.
I sense that you have some fairly strong opinions. I'd like to try to be a little controversial here.
Sure.
What do you think people are doing right or wrong in AI at this time?
What they're doing right is unleashing the power of Moore's law of the modern computer. Again, it's largely old algorithms. That's okay. And it's not really some particular point, something got better. It just looks like the computers got faster and faster and faster. Some of the marketing. But what is wrong here is what was wrong. There's a lot of things wrong. What was wrong also back in the 80s. We have this inevitable hype. The difference was when we had the hype of neural networks equals how the brain works in the 80s. And if you go back and look at those systems and those papers we published, it was just embarrassing. Obviously, that's not how real brains worked, and the classification problems are small. But the difference this time are the big companies like Google. And I'm not talking social media here, I'm just talking about the use of AI. And they do a lot of wonderful things. And they have campuses and they've got a particular take on things. And they just put, I think, an undue thumb on the scale of research in the field in a variety of ways. And I know so many people have been complaints about conferences and that if you want to break it down to educational point, my problem is there's too many people running software that somebody else wrote. You write your own software, roll your own, as we used to say in aerospace, that's different. It's bad enough, and we all do it, but when you run someone else's software, you don't really understand it. But if you're not doing the derivations behind it, and I have found in teaching this stuff literally since the mid 80s in San Diego and at USC for decades since then, that most students cannot derive backpropagation, number one, and wouldn't think to derive it, number two. I mean, to take a simple example, and I throw this out to every listener as a challenge. If you think I'm exaggerating, then just derive backpropagation for soft max output. For that case where the probability is rolling a k-sided die, what you're going to see is the derivative involved is split. It goes two ways. You can do it, and you can go scrounge around in desperation online, and maybe you'll find someone does the complete derivation. But I think if you're going to run it, you should be able to write it and that sort of thing. So that's a problem here. The marketing hype that's come out of it, and the fear in the 80s was realized that there would be a backlash. It was a second neural winner. And there will surely be a backlash. Now, I turn on TV and people are throwing around the word AI. What do they mean by that? First of all, they seem to mean neural network. And then people, if you look at neural networks, they tend to mean, again, just a deep classifier. That's it. That's the brain. That's supervised. That's quite likely not what's happening. And I don't think people 20, 30, 40, 50 years from now will be in any way bound by this kind of thing. You'll be looking back in somewhat embarrassment. So you've got to be careful with that. And I would say in a constructive way, what I recommend in general is, as a student of any field, but of the sciences, derive as many of the mathematical facts as you can find and redirect. Most people haven't derived any. And a good starter is to buy an old calculus book and derive the fundamental theorem of calculus, which requires usually the mean value theorem. See, it does? Yeah, it does. Get in the habit of doing that, not taking this on faith. My bigger complaint, not just in AI neural networks, David, and again, I'm saying this, someone who's been educating this for decades, in my fourth decade of doing it, is what I call faith-based engineering. I mean, faith has a place and it can move mountains, but it does not belong in engineering. It's what crashes planes into mountainsides and leads to bridges falling and creating monsters like deep fakes, which I think corresponds pretty roughly to the coronavirus of AI. You've got to do the derivations yourself, for researchers for sure, and to go beyond that, not just chasing trends. But you can't take it on faith. And it's the nature of tech training in all the STEM fields that it's cumulative. That's not true in a lot of other fields, which, all due respect to my colleagues in the humanities, and I come out of that, that's largely based on opinion in a lot of those. Not in mathematics, not in engineering, not in the hard sciences. It's cumulative. So it's natural to, if you have a 4-year curriculum or 8-year curriculum, to push out some of the fundamentals in favor of the latest trend. And it's led, I think, to a superficiality. It bothers me. I see so many papers with so many authors. Nothing wrong with doing that, but maybe once in a while a sole authored paper or two. You know, the papers I talked about that led to my recognition in the field and such were almost all sole authored papers, done as a kid on an old Corona typewriter that my mother gave me, this sort of thing, with rub-on equations, even worse. Anyway, that's my concern in general. And hopefully in this Zoom age, as we rethink education, we ask questions like, how much do you really remember of your 4-year degree? Most people don't remember. And so as we do that, we can come up with a way of getting more away from faith-based engineering, which I see far too much of. Again, I'm not just picking on neural networks in the eye, but it deserves to be picked on there, but in all fields, and to do it yourself. I might say, for example, I found in this semester, I'm teaching a statistics course, graduate course, been teaching it for many, many years. And eventually I realized people looking too much stuff up in books that for each week I would come up with one main derivation exercise, one each week. And you're to do that several times a day until you see me again the next time. And it may or may not be on an exam, but years later, when you leave the training, David, you can go back and derive that. So for example, this week's derivation is related to neural networks. It's showing how to do the max likelihood derivation of logistic regression. And for the entire course, the main derivation would be to show for an ordinary least squares regressor that's Bayesian, if the prior is normal, that it corresponds to what's called ridge regression or Tikhonov regularizer. It's just a good, but something like that. So as the years pass and the synaptic decay kicks in, which it does all too fast, that you can have some of the technical training. And anyway, I think that'll be that is the kind of thing we'll see more of in the future. I mean, even the idea that everybody sits in the class at the same time and goes through the curriculum. Now, you really shouldn't be proceeding from one module to the next until you get an A in it. And depending on your schedule, that may take longer than other things. But fundamentally, derive it yourself.
I think you're actually touching on my last question here. But what advice would you give for a researcher just starting out in the field?
My first advice, again, is get an old calculus book and do it right this time. You didn't have time when you did it in high school, God forbid, and you forgot it and you placed out of a course in college, or you did it in college. Derive the basic stuff. Go back, and my experience that the stumbling block for scientists is limits. You said, well, why would that be important in something like probability? Well, what's the central result of probability? It's the central limit theorem. Literally that, the tendency of certain aggregate statistics towards a bell curve. And you're not going to get that. A mathematician, it's going to be obvious. For the average engineer, scientist, it's not, even though we're all using that all the time. You're not going to get that unless you have a full command on something like limits. Master the basics. To use a martial arts analogy, and as a kid, in Kansas, where I grew up, I was lucky enough to learn some Shito-ryu karate when I was 11 and 12. I was surprised when I went to the class and learned it, that there weren't all these jumping, flying things that I saw in these wonderful Chinese movies. They were just like 10 basic maneuvers, some kicks and some punches and blocks, and that was it. But the experts had done those kicks, punches, and blocks thousands, tens of thousands of times. Just like a professor tends to have taught the same thing many, many times. But you've got to have that in the tech world. You've got to have that basic repertoire. So whatever it is you're going to do, have that, sharpen that mental sword as much as you can through derivations. I mentioned the late, great Marvin Minsky we brought in, and his advice, and I asked him this once, and he was one of the last students of John von Neumann, for example. He said, go into topology. I said, why topology? He says, it never goes out of style. It's a generalization is set there. Now that may be too much for most people, but it's the right idea that we can't foresee really the coming flux of experience, the kinds of social and personal and other problems society and people will face, but we know some technical tools will be what we have to address them. So get really, really good at that. Not just getting an A in the course, but be able to do it right now in real time, to have it up here deep in synaptic cortex.
Bart, I think that's a wrap. I think I appreciate everything you've been saying. I think that worked out very well. So thank you.
My pleasure, David.